one more video on the Solow model, and that is the Solow model with productivity AL growing over time exogenously. And it's going to be our first sort of brush with balanced growth. Okay, so we're going to get our head round the concept of balanced growth here. So we've got y is ALL to the 1 minus alpha, k to the alpha. And now we're going to go into continuous time, okay, which is kind of nicer mathematically. Sometimes discrete time is kind of nicer for the thinking intuitively about things. Continuous time, typically the math is nicer. So we're going to say that AL dot is equal to G AL. No. So this would say that the number of new, or the absolute increase in productivity per time period, per year, is equal to some number. So then productivity over time would go like that. Yeah. But we don't want that. We want this, which says that productivity grows at a constant rate in percent per year. Exponential growth. Yeah. And the same for the quantity of labor. That's growing at a rate n. And then we've got k dot is, so the increase in the number of widgets per year is the number that you've saved minus the number that depreciate, go up in smoke. Okay. So then we're interested in the BGP. So what is that? Maybe you all know this. I don't know. It's the balanced growth path. And on a balanced growth path, all the key variables grow at constant rates. Okay, this is what a balanced growth path is. The key variables are growing at constant rates, which can be 0. So what are our variables here? They're capital, GDP or production, and these productivities are already given. Yeah, so it's basically capital and production, isn't it? So how do we find the balanced growth path? Typically, we just assume we're on it and then find what the properties must be, given that we're on it. So by definition, on the balanced growth path, k dot over k is some number, right? It's constant. We can call it psi if you like. You probably don't like me using that Greek letter, but whatever. K dot over k is constant. But from this, k dot over k is s y over k minus delta. But that means that y over k is psi plus delta over s, doesn't it? And psi, delta, and s are all constants. So that means that y over k is constant. Which means that y must be growing at the same rate as k. So if k grows by 2%, y must also grow by 2%, right? So that means that y dot over y must also be equal to psi. going to pause there. Okay. So we know that k dot over k and y dot over y are both equal to the same thing, but we don't know what that is. We just made up psi. We don't really know what it is. We know what GAL is, and we know what n is, and we know delta and so on, but we don't actually know psi. So how are we going to make any progress here? We're going to focus on this. So we've got y equal to something, and then we know how fast this is growing, and we know how fast this is growing, and we know how fast this is growing, at least in terms of psi. So then we must be able to say something about how fast y is growing, mustn't we? But what can we say? How do we do that mathematically to work out how fast y is growing given how fast these things are growing? So we want to know dy dt, don't we? dy dt, that's like y dot, isn't it? That's the same thing as y dot. And actually we want the growth rate of y. So we want dy dt over y. But we'll get that later. So what is dy dt? How fast does y change over time? Well, it's going to depend on how fast y changes when AL changes, multiplied by how fast AL changes over time. So if AL is constant over time, then this is 0 and this term makes no difference. But if AL is growing, then we need to know how much it grows and how much that growth affects y. The product of those is the answer. And then we've got the same thing for L and K. dy dl times dl by dt plus dy dk dk by dt. So this is the total change in y over time. It's the sum of these three effects, right? Because each of these things growing will push y up, won't it? So to get the total change in y over a time period, we need to add up the three effects of these three things changing. That's what this is. Okay. So what is dy by dAl? It is 1 minus alpha times y over AL. And what is the AL by dt? It's just AL dot, yeah. And what is dy dl? It's 1 minus alpha times y divided by L. And what's this? That's just L dot. And what's dy dk? It's alpha times y over k. Times k dot. And this is y dot, isn't it? So, why don't we divide through by y to get y dot over y. And then we shift these on top of each other and we get 1 minus alpha times AL dot over AL, which is GAL, plus 1 minus alpha L dot over L, which is N. And I can put that in the bracket like this. 1 minus alpha GAL plus 1 minus alpha L. Plus alpha k dot over k. But k dot over k is the same as y dot over y, isn't it? So if we take this over, we end up with 1 minus alpha y dot over y equals 1 minus alpha GAL plus n. Cancel these out. Y dot over y is equal to GAL plus n. So that is the growth rate of production. It's the sum of the growth rates of productivity and the labour force or population. If population's stable, production just grows at the growth rate of labour productivity. What about if we had little y, where little y is big Y over L, production per person? How do we work that out? Well, let's do the same thing here. How does little y change with time? The little y by dt is the little y by dy, big Y, the big Y by dt, plus the little y by the L by dt. So little y dot, the little y by the big Y is just little y over big Y, isn't it? dy by dt, that's y dot. The little y by the L, this is L to the minus 1, isn't it? Let's write this as big Y times L to the minus 1. We got minus 1 times little y divided by L. So we've got minus little y over L dot. Divide through by little y, we get little y over y equals big Y dot over y minus n. So the growth in production per person is simply GAL. So when we look per person, we lose the effect of population growth. Okay, so the methods there in terms of differentiating an equation with respect to time, super important. Okay.